Hi everyone, it's my great pleasure to introduce Kasia Wyczesany, who is at ICE and Brown this semester. She's going to tell us about optimal transport. Kasia, please.
Thank you so much. Thank you for inviting me. It's a pleasure to be here, I suppose, in Iceland at the moment, but with all of you. I'll talk, as Thomas said, about optimal transport, but with respect to non-traditional costs, by which I mean costs that may attain infinite value, and that will be important. The work that I'm going to present here is joint work with Shiri Ercztein-Avidan and Shai Sadowski. And I apologize to all of those who might have seen parts of this talk or similar talk, but I thought it's the most suitable topic for the probability and analysis seminar, and I hope you'll find it interesting. I know the optimal transport is not the mainstream topic in this seminar, so I've prepared an overview. There will be an introduction, and I'll keep coming back to introductory elements anyway throughout the talk. Also, please feel free to stop me at any time and ask questions. That would be really nice. I'm going to keep it light, I hope. So after a few slides of introduction, I'll talk about cost-induced transforms that are really much linked to the problem, but also they are interesting on their own, actually. Then I'll talk about the link of optimality and C-sub gradients and what the C-sub gradients are. I'll then present our main results and elements of the proof. I hope we'll fit all of that in. Okay, so transport maps and plans. We are interested in probability measures, and I will be talking here mostly about Rn, but in general, you can consider Polish spaces. Most of the theory holds there. But for simplicity, think Rn. We'll be considering a cost function, which is just a function on the product space, Rn times Rn, right? And it can take a plus infinity value, but it cannot take the minus infinity value, okay? So that we can have a plus infinity here. And we'll be wanting to transform mu to nu. And what a transport map is? A transport map is a function such that for each set A in Rn, we'll have that the mu of the inverse of A is equal to the measure nu on that set A. That's, I'm sure everybody has seen that before. And those transport maps are really important and really useful in especially convex geometry for mentioning an important result. So that would be Brenier-McCann, which tells us that if your cost function is a quadratic cost, which I'll say a bit more about a little bit later, then your transport map always exists and is given by a gradient of a convex function. This has big importance. It also allows you, for example, to give a nice proof of a Brun-Minkowski theorem using those tools. So this is really quite nice. But you cannot always expect a transport map to exist. For example, if you have measure mu, which has just one atom and the weight 1, and measure nu has 2 atoms, the map would have to split that atom, and that's not allowed obviously by a map. So we have to generalize this notion to transport plans. And we'll say that a pi is a transport plan. Here, pi. If it's a measure space, it's a probability measure on the product space, and it has the property that mu and nu are its marginal. So for any measurable sets A and B, we will have that pi of A times Rn as mu of A, and similarly for the second projection. Okay. So these are transport plans. Okay, so when we want to, so where the problem generally comes from? It comes from a guy called Gaspard Monge. He was a French engineer, mathematician, but also educationalist, I suppose is the word. He was involved in the French Revolution, and he was wanting to build like a safety piles of sand around the city. So he asked himself, okay, what's the cheapest way or like most cost-efficient way to transport a pile of sand from one place to the other, say, okay? And then he asked, of course, what is the most optimal way to do that? And what do I mean by optimality? Optimality is given a cost function, which for gas-powered motors was just the distance where the particles need to be transported by. The total cost of a plan is given by this integral here. So integral of the cost over the plan, right? And then the optimal plan is the one from which we get an infimum over all plans with marginals mu and mu. Okay. So a natural notion in optimality, in some sort of geometric way to imagine this, is the notion called cyclic monotonicity, and the definition will show up in a second. But in brief words, what does this mean? If I say have a measure mu that has 3 atoms, and I have a measure nu that also has 3 atoms, say each have weight 1/3, right? So that they're both probability measures. Then optimality means that the coupling that you've chosen, say this is your coupling, you couple points on the same height. The sum, and each of those transportations has some certain cost. So say those edges have weights, weight 1, weight 2, weight 3. And optimality would just mean that this plan that you've chosen is better than, for example, than any other one, right? So that could be my, I don't know, W1 prime, W2 prime, and then I would have to transport this guy. So W3 prime, right? And this is exactly what the cyclic monotonicity tells us about. So here's the definition. The definition is for any set, doesn't have any measures in it in this definition, because you should think about the set, the G, as support of the transport plan, okay? So because this is a set in a product space, and we'll call it cyclic monotone if for any points in G, we have that their cost, the cost of the transportation of such pairings is finite, first of all. And second of all, for every m tuple of those points in G, so the set that G can have infinite amount of points, but for any m tuple, we'll have that the sum over a cycle, and this is exactly what I drew, right? So this is the cost of your matching, you've chosen one, and this is some permutation. And this definition with the I+1 versus x sigma I, they're equivalent definitions, you can always relabel, right? So this sum must be less than or equal than 0. Then your matching or your plan is optimal, okay? So this is in some sense a geometric way to think about optimality. Okay, so just let me tell you what is briefly what is the difference when we allow cost to take the value plus infinity, okay? So I have 2 measures again. Here I drew the spaces x and y, and these are my probability measures. They are discrete. In the case when we are having a cost that is real valued, we would say that we have all the edges between all the points. So this could be all the edges, and the weights of those edges are always finite, right? Are always real numbers. So I can draw them all. I'm not going to draw all of them, but you know what I mean. While in the case when we have infinite values, you can just imagine, oh, sorry for that. We can imagine that some edges just simply don't exist. So you could have just, oh, that's a weird. We have a black, okay, and a green. So we could have only some edges that exist, right? So say the edges that I drew have finite weights, okay? This means in particular that some transport schemes are simply prohibitive. You don't want, if you're looking for an optimal plan, you will never want to transport this guy to this guy here, because there is no edge which has finite value, okay? So that's what we are interested in, and I'll tell you our motivation for such a problem in a second. But what the situation tells us is that we need certain, there are certain necessary conditions on the 2 measures involved for a transport plan for the transport plan to be possible, for it to be finite, have a finite total cost. Okay, so this is what Holzmer's theorem tells us, right? Because if I had those measures here and here, It just tells us that whatever neighborhood of points here I choose, so this is the set A of elements here, then the number of points to which these guys are connected to must have cardinality at least as large as the number of points here, right? This is Hosmer's theorem. This is for discrete measures here, this translation, but one can reformulate this and have it in some sense continuous for any measures mu and nu. So the condition becomes on the measures that mu of A must be less than or equal than the nu of the measure of the set of y's such that there exists an x with the finite cost. So that is basically what I drew before, okay? That's for all A subsets of x. So these are sort of necessary conditions for the two measures. We call them compatibility condition, right? So measure mu and nu will be compatible if such inequalities are fulfilled. So this is an obstruction in this transport problem with cost B attaining infinite values. All right. But let me get back to optimality for a second. So here is the definition again of the total cost. And it turns out that one can reformulate the problem. And this is the topic of the Katarzyna theorem, which says that, so we need a condition on the cost, which is that it is lower semi-continuous, but it can take infinite values. We have some probability measures mu and nu as always. Then this notion here, this infimum defined above, is equal to a supremum over all those functions phi and psi, which sum up pointwise to less than cost at the point xy. We call such pairs admissible pairs, okay? And the supremum, this theorem says that in fact we can look at the supremum. So this is Katarzyna duality theorem, for which I believe he got a Nobel Prize. Okay. Yeah. So one immediately starts to wonder, what is the larger admissible partner for a guy? So I have my functions phi and psi, which are admissible. Then the largest function psi can be given by the C transform of the function phi. And that is, we define the transform phi C at y to be the infimum over x's of C of xy minus phi of x. And I believe it's clear from the definition that, first of all, phi and phi C are always an admissible pair, okay? That the C transform is order reversing, right, pointwise. So if phi of x is less than equal than psi of x for every x, then we'll have that phi c of x or of y will be greater or equal than psi c of y. All right. Then we'll have, of course, that if you phi and psi are an admissible pair, then psi will be always less than equal than phi c. This is just following from the definition. And finally, it follows that the C transform is a involution on its image, okay? So I have that phi is less than equal than phi cc, this follows from the definition, and therefore we can incur, if I apply C to both sides, I will get phi c by order reversion, this will change order, right? Phi c, c, c. But on the other hand, I can also apply this definition to the function phi c, right? So this is phi c somewhat. And this is phi c, cc, which gives us the equality. So we have a class of functions, the image class, we will call it the C class. And these will be an important classes of functions for the given transportation problem with the fixed cost, right? Let me call a function of the, so phi say of x equal C of x y naught plus beta. These kind of functions, so beta is some sort of constant here, we'll be calling them basic functions. So those basic functions always belong to the class, and using them as an infimum of such functions will also belong to the class, and therefore they will be building blocks of how one can obtain such C class functions, okay? So, having all that in hand, I would like to give you some examples, right? So that we can see a little bit better what those C transforms do. So first of all, the promised quadratic cost. So it can be, sometimes it can be viewed without the over 2, and sometimes it can also, the name quadratic cost can refer to the minus scalar product xy. And I'll tell you in a second why. But let's see what the C transform does, okay? So I have phi C of y, and I have the infimum as in the definition. I have the cost written out here and the function. Then I pull out y squared because obviously it does not depend on x. And what we see here is a Legendre transform. So a Legendre transform is given here below, but I'm sure everybody have seen that before. And therefore, we know what the image class is. We know that this Legendre transform always gives us a lower semi-continuous convex function. So the class is clearly y squared over 2 minus a convex function, right? So plus a concave function in this case. But why did I say that this cost can be replaced by the scalar product? So if I've gotten rid of those guys, we would get the other cost. You'd also get the Legendre. And what's important here is that all those guys would cancel out if you'd consider cyclic monotonicity. So when you talk about optimality of the plan that is optimal for this quadratic cost here and for quadratic cost here will be exactly the same. The functions you obtain are slightly different, but this is because how the image class looks like. Okay, so now another cost, an example. In fact, our favorite example and the motivation for the whole project actually is the polar cost. So I say P here because this is our favorite cost, so we will distinguish it. And this is a minus logarithm of scalar product x dot y minus 1. And this little plus here means that I just mean maximum of x dot y minus 1 and 0. So this cost attains infinite values, right? So whenever the scalar product is less than or equal than 1, we'll have that the cost is infinite. And the P transform, so this polar transform, is linked to the A transform, the polarity transform, which was sort of promoted by and discovered by Shiri, Avidan, and Vitali Milman. So this is in some sense a starting point of our project, and that's how the polar cost came into this whole thing. We realized this dependence, right? Okay, so now I will go back again to optimality and tell you a little bit more about how Kantorovich duality theorem that I've mentioned already helps us to find the right plans and maps. So obviously we will always have this inequality because phi and phi c are admissible, right? But to find an optimal plan, we'll need equality here. And this is in some sense an object of the next definition, which is that of C subgradient. We'll say that for a function phi, which can take values minus and plus infinity as well, and for a given cost, its C subgradient of a function phi is the set of points xy. So this is a set in the product space such that phi of x plus phi c of y is equal to c of xy, and it is finite. All right. So obviously, and we'll denote phi c subgradient, C subgradient of phi at x to be a section. Okay, so there will be the y's for which this holds. And we can, of course, define it for phi c and so on. Note that for a quadratic cost, so the standard example in some sense, the C subgradient becomes the well-known subgradient, right? And in the differential case, this becomes the derivative, of course. Okay. So having the C subgradient, I'm coming back to the notion of the cyclic monotonicity. So to tie the optimality and the subgradient, okay? And so this is just a reminder that the set is cyclically monotone if, and here I wrote it slightly different, so I moved the mixed guys, the other transport plan to the other side, right? So your choice must always have a smaller total cost than the other for any M tuple. And it turns out that if you give me a C subgradient, such set will always be cyclically monotone. And this is not hard to see, and I'll prove it very quickly so that we're on the same page. So what it means for a point xy to be in a subgradient, it means that phi of x plus phi c of y is equal to c of xy, right? So what we have is that for every, so that the infimum, I'll be writing out the definition of phi c, okay? Infimum of the w of c of w y minus phi of w is equal to, and I'm moving phi of x on the other side, c of x y minus phi of x. Okay, so what infimum means, if the infimum, if the equality is achieved on the infimum, it means that pointwise for every w we have this inequality. So rewriting this, I can write that for every w, I have that c of, and I'll switch sides a little bit, c of x y minus c of wy is less than or equal than phi of x minus phi of w, right? So now letting x to be xi, y to be yi, and w to be x, say sigma of I, we get, and when we obviously sum everything up, we'll get exactly that c of xi, yi minus c of x sigma I yi is less than or equal the sum of all those guys. But then what happens is that every element shows up in the first place with a plus and in the second place with a minus, and therefore we get a 0. And that tells us that every C subgradient is cyclically monotone. So an important question is the other direction true? Is every cyclically monotone set contained in the C subgradient of a function, of the C-class function? And this is an object of the theorem by Rockefeller, Rochet, and Ruschendorf that says that, yes, in fact, we have that if the cost is finite valued, and this is important here, that the cost is finite valued, then a subset, a G subset of a product space is cyclically monotone if and only if there exists a C-class function for which G is a subset of its subgradient, C subgradient. And Rockefeller proved this theorem for the quadratic cost. Rochet and Ruschendorf generalized it to other finite valued costs independently, I believe. And their proof just follows from the construction. I mean, they literally give you a function. They write out an infimum, they do the cyclic thing, and it turns out to be important that the cost is finite valued, or else the thing doesn't work. So we wondered what's happening when the cost attains infinite values. Well, first of all, we have a counterexample with our polar cost, saying that there are polar cyclically monotone sets which do not admit a potential. And this is very easy to see again. So you'll have to believe me that in one dimension, p-cyclic monotonicity means that the set lies on a graph of a decreasing function. So this is an example. And I can take 3 points on it. So I can take, say, this will be y1, x1, y1. This will be x2, y2. And I'll take here a point. I'll call it zw. But this will be a traveling point, traveling towards the boundary. So in this polar case, I told you that if the x dot y minus 1 is less than equal than 0, then we have infinite values. So everything below this blue thing means you start being infinite. Here you're finite. Okay. So how to see that this set does not have a potential? Very easy. We write out the definition, of course. So for every u, we must have being in a C subgradient of a function. So assume there is a phi that is a potential. We'll have phi of x minus phi of u greater or equal than C of x y minus C of uy. And now we can plug in x1, y1, and z. And we can plug in separately z, w, and x2, these two, like from those pairs. And if you plug this into this inequality and sum it up, you will see that what you get is on the left-hand side, it does not depend on z. So the things cancel and you get phi of x1 minus phi of x2. While on the other side, you get something that includes c of zw. And that means this is a fixed number, which is a real valued number, and this guy goes to plus infinity. So clearly, then there cannot be a potential. And this is a counterexample. So we wondered, what is the sufficient and necessary and sufficient condition? What is the sufficient condition for an existence of a potential when cost takes infinite values? And here's our theorem. We can now take a cost function which has infinite values, obviously. If you take any set G, which is a subset of the product space, then there exists a C-class function such that the G is a subset of its C subgradient, if and only if G is C-path bounded. So let me first draw it, and then I will show you the definition. So C-path boundedness is very similar to C-cyclic monotonicity. In C-cyclic monotonicity, we were adding your matching, our chosen matching, and subtracting some other matching. So now I'm drawing this way. Okay. Now in C-path boundedness, what we need to do, we need to find a bound on just this parts of the path. So you're fixing your starting point. So this is start, this is finish. And then for any path through any other points in G that looks like this, will have to be bounded by some number that depends only on the starting and finish. And let me show you the definition. We'll have, for any starting point and end point, as I said, we'll have a number that depends only on those 2 points. I'm repeating this because this is an important definition, of course. And then for any m-tuple points for which participate in the path, we'll have the sum. And now instead of having all the points, we finish a bit earlier without the last one. And we require to have the bound m, which will be a positive number, of course, but we don't mind that. Okay. So first thing to note is that the C-path boundedness implies a cyclic monotonicity. So if you're starting and ending point was 1 point, so say this is your start and a finish point. And it would turn out that on a cycle, so you're not cyclically monotone, on a cycle, you have a path which has a positive sum, not less than equal than 0, right? Then you can go on this path over and over, right? And accumulate as much as you want. And therefore, the path will have an arbitrarily large sum. So C-path boundedness implies cyclic monotonicity. Also, for real valued costs, cyclic monotonicity and C-path boundedness coincide. So I'm writing out the cyclic monotonicity condition here, right? And then if my cost is real valued, I mean, anyway, I can move this guy over here. And if the cost is real valued, this will give me a bound, right? I can then go through any path that finishes at this place, and this will give me the bound. But it's very important because the cost is real valued because this guy a priori could be plus infinity, and then the bound is not valid. Okay. I hope if you have any questions, please interrupt me. I'll keep going for now. So what we did here, so this will be in some sense path towards the proof. What we did here was to show that there is a different way to look at the potential. Instead of trying to construct it as Rockefeller, Rochet, and Ruschendorf did, we can consider the problem as in a problem of solving a system of inequalities. So what we have here, if we fix a cost, which can take infinite values, and we have some set G in the product space, then the potential exists for the set G, if and only if the following system of inequalities, so here we have inequalities, right, has a solution phi, where x and y, so you can see that it's slightly funny in the sense that it takes a whole point and then a half point. but this really doesn't matter. If you use the W, you can add the whole point in G as well, and it doesn't cause any problems, of course. So it's actually not very hard to see why this reformulation is sufficient. So I'll show you one direction how to show this. So if you had xy in phi c of phi, then which is also, so it's in G, right? Then what we would have is that phi of x plus phi c of y is equal to c of xy. So I'll rewrite it as c of xy minus phi c of y. But also for every z in this projection of G, okay, we must have that phi of z obviously is an infimum over some w's of c of zw minus phi c of w, right? Okay, if it is an infimum, then it must be less than or equal than if I choose some point. So if I choose zy, if I choose y for this, I'll have the inequality. Now I can add those, right? And if I add it in the right way, so if I'll do phi of x minus phi of z, I have one phi of z here, so I have this minus this inequality, right? Then this changes, and we have minus phi c of y and then plus phi c of y, they cancel, and therefore I have c of xy minus c of zy. And the other direction isn't much harder, so I'll leave it at this. But this means that, in fact, to find a potential, I just need to make sure that there exists a solution to this system of inequality, which I can, of course, consider in an absolutely abstract setting. And so I can rewrite it as inequalities on numbers alpha ij, and alpha ij now will be numbers that belong to, they can be minus infinity, but cannot be plus infinity, right? Because this guy, if xy was in G, this is a real number. This a priori could be plus infinity, right? So I have a minus, and therefore alpha ij can take value minus infinity, but cannot take plus infinity. And I will say now, instead of considering a function, I'll look for a vector, right? So I'll have a vector with entries eta I and eta j, and I need the solution for this system. So first of all, observe that this inequalities, so having a solution to this system of inequalities will give us the C-path boundedness, right? Because I can just sum up the alpha i's, and the eta ij's will collapse into just dependence on the two guys from which we started. Okay. Okay. So we have to prove the following theorem: that if I have coefficients alpha ij that can be minus infinity, then the system of those inequalities here has a solution if and only if. So this is our condition of the translated C-path boundedness. If the sum of alpha I, so if for any m tuple of points, so for any path, right, for any m tuple of points, we'll have that the sum of alpha I1, and those guys in between, and then the final guy alpha IM alpha j is less than or equal than m, and m depends only on I and j. So let me just mention one thing. In case when the cost was real valued and alpha ij could be only a real number, so it couldn't be minus infinity anywhere, this is in some sense showing that this is true is relatively easy compactness argument. And it starts becoming a little bit more tricky in this case, of course. So instead of proving this theorem directly, I will reformulate it yet again. And I will replace it by a theorem that seemingly looks a bit weaker. So I still want to solve a system of inequalities. Now I'll be writing Aij instead of alpha, because the condition on A's is slightly different. I want the sum of ik plus 1 of those guys to be always less than or equal than A of I1 IM. Okay. Those two statements are entirely equivalent. but it's a little bit easier to obviously show this. And I mean, you can, it's obviously you can read it in our paper how to show this. But what happens in fact is just you define aij's in a way that depends on those alphas, and this is just like a supremum of the sum of alpha ik plus 1 over all those m tuples and all the paths, right? So that's more or less what is happening here. So now I will try to prove this theorem here, and it will use Zorn's lemma. So we'll start by checking the conditions for Zorn's lemma. So let me start by saying what kind of things we are considering here. So we have our index set I here. So I will be consider a set of partially ordered set of pairs. So pairs will be fj, j, fj, such that j is a subset of I, and fj is a function. So now again, instead of those eta ij's, I'm coming back to functions. I can see now that maybe that wasn't a good thing to go back and forth, but I hope you can stay put and follow this. So you will have now a function fj, which takes a index, so and gives me a real number, and it must fulfill the inequalities, right? So we must have that for every ij, fj at I minus fj at j is greater or equal than aij. Okay. So we will, first of all, the set of such pairs is not empty, right? Not empty, because we can take one element. So I can take some I0 and choose any constant, and I'll be okay. Oh, let me mention what the partial order here is. Partial order. It's simply that, so we'll say j fj is less than or equal than k fk if j is a subset of k in a normal sense, because this is a set of indices, and moreover fk on j. So if we restrict fk to j, it's equal to fj. Okay, so now we need to check the conditions of Zorn's lemma. So we need to check that every chain has an upper bound. So okay, so let me write that j alpha, fj alpha, and alpha will be in some subset A is a chain. And of course, when I say chain, I mean that all elements are comparable. And let j to be union over alpha, j alpha, and let fj to be the union over alpha, fj alpha. That means that we extend where it wasn't defined before. Okay, and so this is well defined because of the chain property, right? So this all coincides and makes sense. Okay, so now if I have a pair j of j, right? I want to say that it also belongs to our set. So that will be if we have I and j in j, okay, then it clearly belongs to our set, because then there will be existing an alpha such that I, j are in j alpha, and therefore we'll have this inequality fj alpha at I minus fj alpha at the j greater or equal than aij, just from the property of fj alpha, and so fj also fulfills it. Okay, and finally, obviously, this guy j and fj is the upper bound on our chain. So we can use the Zorn's lemma, and so by Zorn, there exists a maximal element, and let me denote it by J star Fj star. Okay, so what remains to show is that J star is equal to I, right? So we had a set I here, and we want to say that J star can be the whole I. So towards a contradiction, so towards a contradiction, assume that I is not equal J star. That is, there exists an I in I, which is not in J star. Okay. Then, if we can extend Fj star, if can extend Fj star to be defined. Let me write it I0, defined on I0 in a way that will still preserve all the inequalities, then we will contradict maximality, and we'll contradict the maximality of J star, and therefore we'll finish it, right? So let me write what inequalities this extension would have to fulfill. So we would have to have that A I0j is less than equal than f of I0 minus f of j, and A of j I0 would have to be less than or equal than f of j minus f of I0. Okay, so, and this would have to happen for all j in J star. So in other words, I can rewrite this, and I can say that we must have that the supremum over j of A I0j minus f j star at j is less than equal than f of I0, and also the infimum of over j's of A j I0 minus f of I0. Is this correct? F of this, no? So this is infimum over Aij. So what am I doing? I wanted this to be Aij0. Okay, no, it was all good. Minus f of j. And no, I feel like j f Ij. Ah, yes, yeah. Sorry for that. So, right. So I'm now putting this guy on the other side. So I have f of j minus a j I0. So what happens is that I need all of those inequalities to hold, and in particular, this means that I need to have a I0j plus fj star j less than equal than f of j star of k minus a k I0, because I'm getting rid of here of the infimum of the supremum. So this needs to hold for every j and k. Did I leave another slide free? Nope, I didn't. So I'll finish on top here. I'll just erase this. I hope that's okay. Okay. Oh, sorry for that. Okay. So I need those inequalities here. I'll start them to hold for every j and k. So let me rewrite it slightly, but write it in a little bit nicer handwriting. Sorry for if that's not very legible. Then we have, so ai0 j plus ak I0 is less than equal than fj star. So I plugged in j star here. I hope you didn't mind. So first I didn't write it, and then I did, because what I meant is that this has to happen for all j's in j star for already defined f. So we'll have that the restriction of the f that one wants to get needs to be equal fj star here. Okay. This is at k minus fj star at the j. So we would need this inequality to happen for all j, k, and j star. But good news, by our assumption, we have that akj is greater or equal than ak I0. In fact, any element I can choose here. Erase this dot here. We can choose any element here plus ai0j. This looks a little bit like a triangle inequality for the indices. So, but we do have that, and we know that, we know that fj star at k minus fj star at we have j is always greater or equal than akj. So as you can see, that means that this guy is always less than or equal than this, and therefore is less than equal than what we had to prove. And this finishes the proof that the CPAP boundedness is the sufficient condition of for existence of a solution for the system of inequalities. And I believe I'll finish here. So thank you very much.
Thank you, Kasia, for the talk. I wonder if anybody has any questions at this point. So the proof seems to be non-constructive.
Yes.
Right. Are there some special cases where it's constructive, or I mean, can be made constructive?
When the cost is real valued, or when your whole set G is far away from the infinite set, because then you can consider a restriction of that cost and treat it as it was finite value. We have a different proof of this. Actually, this proof came as 10 days before I was submitting my thesis, and my thesis came in with the first proof, which was significantly harder. I went through some serious combinatorics and the graph theory, in fact, but also used, in some sense, it used Hanbanach, so it really used Soren's lemma as well. So we don't have a constructive proof of that.
Okay.